Have you ever stopped to think about how massive internet applications, the Twitters and Amazons of the world, how they just stay online? To most of us, the internet feels almost like a natural resource, right? Like turning on a faucet. But under the hood, oh man, these systems are operating under absolutely immense pressure, handling just unimaginable volumes of traffic and data. Welcome to The Explainer. Today, we're diving into the masterclass principles of designing data-intensive applications and looking at exactly how the best engineering teams in the world keep their systems from simply collapsing under their own weight.
Okay, let's take a quick look at the roadmap for today. We'll kick things off with the data-intensive shift, then move into designing the data system. From there, we'll unpack reliability, tackle scalability through a fascinating real-world challenge from Twitter, and finally, uncover the truth about latency.
All right, kicking off with Section 1, the data-intensive shift.
Historically, if your software was slow, the bottleneck was mostly about raw compute power. You just needed a faster CPU. But to understand the modern shift, we're drawing directly from the definitive guide on this topic, Martin Kleppmann's Designing Data-Intensive Applications. If you're in the engineering world, you probably know this affectionately as the O'Reilly Wildboar book. Honestly, this text is essentially the ultimate developer toolkit for understanding how to build reliable, scalable, and maintainable systems.
So, what's the actual difference? Well, an application today is considered data-intensive if the primary challenge is actually the data itself. We're talking about the sheer quantity of it, its complexity, or the blistering speed at which it's changing, rather than just raw CPU cycles. Back in the day, you might have just written some code to run on a single machine and called it a day. Today, developers aren't just writing code anymore, they're acting as full-fledged data system designers.
Which brings us right into Section 2, Designing the Data System.
Let's pull back the curtain a bit. When a user interacts with an API, that API is usually doing a really good job of hiding a massive amount of complexity from the outside world. Because a modern application rarely relies on just one simple database anymore. Think about it. You've got application code, managing an in-memory cache to instantly serve read requests, a primary database acting as your core system of record, a full-text index to handle complex search queries, and probably a message queue for asynchronous tasks. Stitched together, all these individual components form a completely new, special-purpose data system.
To evaluate these complex composite architectures, we generally rely on three overarching system pillars. First up is reliability, meaning the system works correctly even when things go wrong. Second is scalability, which means it copes efficiently with growth in data or traffic. And third is maintainability, ensuring it's easy for diverse teams to operate and adapt over time. Today, we're really going to zero in on those first two pillars, starting with reliability.
Moving to Section 3, reliability and tolerating the inevitable.
When you're dealing with massive scale computing, you kind of have to accept a hard truth right out of the gate. Something is always broken. It's literally impossible to build a system that prevents everything from going wrong. To really grasp this, we need to bust a common myth and clearly distinguish between a fault and a failure. Okay, so a fault is when one single component of your system deviates from its spec. A failure, on the other hand, is when the system as a whole stops providing the required service to the user. Our goal isn't to prevent faults entirely because, again, impossible. It's to design fault-tolerant systems that prevent those faults from cascading into total failures. Actually, counterintuitively, the most resilient systems deliberately trigger faults. Take the Netflix Chaos Monkey, for example. It intentionally kills individual processes without warning, just to ensure the system's automated recovery machinery is continually exercised and tested in the real world.
Let's break down the types of chaos your system is inevitably going to face. First, we have hardware faults. In a massive storage cluster of, say, 10,000 disks, basic statistics tell us you should expect one disk to die every single day. We mitigated that with redundancy and rolling upgrades. Then there are software errors, like the infamous 2012 leap-second bug in the Linux kernel that caused a bunch of different applications to just hang simultaneously. But here's the really surprising fact. Humans cause far more outages than hardware failures. Yeah, one study actually found that operator configuration mistakes are the leading cause of outages. We basically have to mitigate our own human error using safe sandboxes, really thorough testing, and easy, rapid rollbacks.
Next up, Section 4, Scalability and the Twitter challenge.
Here's the thing. Even if your system is perfectly reliable today, a massive spike in load can absolutely break it tomorrow. But to have a real conversation about scalability, we can't just vaguely say a system scales. We need concrete load parameters. Let's look at Twitter's load parameters from around November 2012 to make this real. At that time, users posting tweets generated an average of about 4.6 thousand writes per second. Okay, not bad. But users reading their home timelines, that generated 300,000 reads per second. Just contrast that relatively manageable volume of users posting new tweets with the absolutely massive, crushing load of users requesting to read their timelines.
So, here's how Twitter initially approached this problem using a standard relational database schema. When you requested your home timeline, the system would find everyone you follow, fetch all their tweets, and merge them all together sorted by time. It's a standard SQL join operation, right? But doing that massive computation on the fly, it struggled immensely under the weight of those 300,000 read requests per second. The system simply couldn't keep up with the load.
And this brilliantly illustrates how fixing one problem can create a fascinating new one. Twitter ended up shifting to a fan-out data pipeline. They essentially created a dedicated cache, think of it like a pre-computed mailbox, for every single user's timeline. So when someone posts a tweet, the system immediately pushes it into the timeline caches of all their followers. This brilliantly solved the read problem. Reading the timeline became cheap and instant. But it created a massive fan-out write challenge. Imagine a celebrity with 30 million followers posts a single tweet. That one tweet results in 30 million writes to home timelines that all need to happen within about 5 seconds. At the end of the day, scalability is really all about carefully balancing these architectural trade-offs.
Finally, Section 5, the truth about latency. Let's shift gears a bit to understand performance under extreme load. First, we need to clarify another commonly confused set of terms: latency versus response time. Response time is what the client actually sees and experiences. It includes the time it takes to process the request, plus any network delays and queuing delays. Latency, on the other hand, is strictly the duration the request spends latent, just waiting to be handled. So, if we want to accurately measure the actual end-user experience, we absolutely have to look at response time.
And why does measuring this accurately matter so much? Well, let's raise the stakes. Amazon has actually observed that a mere 100 millisecond delay in response time translates directly to a 1% drop in sales. Just think about that. A tenth of a second. Measuring performance and speed actively translates to the bottom line. Literally every single fraction of a second counts.
Now, what's really interesting about this is how it completely debunks the myth of the average response time. When you look at a distribution graph of response times, sure, most requests are fast, but you always have these huge spikes, the outliers. Relying on an arithmetic mean or an average hides these outliers entirely. The true metrics that actually matter are your higher percentiles, the 95th and 99th percentiles, which we call tail latencies. That 99th percentile tells you the response time experienced by the slowest 1% of your requests. And guess what? Those slow requests usually belong to the customers with the most data on their accounts, which means they are the ones who have made the most purchases. So your tail latencies are directly impacting your most valuable customers.
We've covered a lot of ground today. The modern shift to data-intensive architectures, the core pillars of reliability and scalability, the fan-out challenges of Twitter, and the hidden dangers of tail latency. Designing these systems is a complex, constantly evolving masterclass in trade-offs. So I want to leave you with this final, provocative thought to apply to your own engineering architecture. If your application's load spiked by 10x right now, which component would break first, and exactly how would it fail?